Okay, so this is after Kirk and Spock and the Enterprise are going to go explore the nebula. And gosh, so let's watch. The nebula is so dense that they can't go around it. So the nebula is so dense they can't easily go through it, and it's so large they can't go around it. Interesting nebula. Let's listen to what they say.
Our mission is straightforward. Rescue a crew stranded on a planet in uncharted space. Our trajectory will take us through an unstable nebula, one which will disable all communication with Starfleet.
So Kirk says, we have to go through the nebula, can't go around it, and it's going to interrupt communications. So, and just looking at it, it's so dense we have to navigate through it like it's challenging. So it's got to be big, so I can't go around it, but it's got to be dense, so it's dangerous and blocks communications.
That's right, because a normal nebula is like 99.99 something percent just hydrogen,
right?
And then a little bits of helium, and then a little even smaller amounts of like lithium, boron, other heavy elements.
Right? Yep.
And so for a normal nebula, you could probably just punch through it. It's thin. It's very thin gas.
Right.
You can see through it. Not a problem. And so, but they're big. So could be several hundreds, thousands of light years. I'm not sure about those numbers. Don't quote me. Yeah. And so I could see how it'd be hard to go around it. But on the other hand, Starfleet has warp capabilities. So,
right.
I mean, maybe just go around it, right?
Right.
So this is like a magic nebula. It's so big that they can't go around it, even though they have warp speed, but also so dense that they can't just zip through it, no problem.
How big is this nebula? Like, what's the mass of this nebula? And
let's
do it. Let's do it.
Okay, so our goal is to estimate the mass of the nebula.
Yep.
And so our knowns is a bullet point that we didn't flesh out.
Yeah, I think we don't. Well, we don't have any knowns actually.
We don't have any knowns. Okay, that's right.
We have to guess densities and masses based on the Enterprise and other things they've just said. So
let's make some reasonable estimates. See what we get. So if we want to figure out the mass of the nebula, we need to know the mass density of the rocks. Yep. And while we're not there, we don't know what these rocks are. We can estimate it, maybe Earth-like rocks. And so that's 5,500 kilograms per meter cube. And there are some rocks that are more dense than others. There are some rocks like shale that's a fairly low density, but not like a factor of 10 to 100. And where we're going to get to, even if we've underestimated by a factor of 100, not going to matter.
Yeah, it doesn't matter. And certainly from the pictures, it looks like rocks. So we're not talking we're not talking like diffuse gas. We're talking rocks.
Solid objects that the Enterprise needs to worry about. Even if they have shields, they need to worry about getting banged up. Okay. So if we know the mass density of the rocks, if we know the volume of the rocks, then we can figure out the mass of there. Mm-hmm. And so this is a bit tricky. We'll estimate it as the length of the Enterprise, and let's support that. Yeah. So here, from this picture of the nebula, a little bit tricky because there's some forced perspective. These rocks are closer, and these rocks are farther. Either way. Yeah. And so let's try to look in the same plane, the same like rectangle as the Enterprise. So the Enterprise, we looked it up, is, what did we say? It was 300 meters?
300 meters, yeah. Looked it up on...
289, 300.
Yeah.
And so the nebula needs to be dense, but not too dense. If it's not dense enough, then the rocks are far apart, and Sulu's like, yeah, no problem, I'll just fly through this, right? If it's too dense, then it's like it's getting closer and closer to a solid wall, and Sulu's like, we can't even do this, we gotta just go around. Yeah. So that means that the distances between the rocks, they need to be Enterprise-ish sized, right?
Yeah, so we were estimating that the rocks, if we look at that picture, if we look at the size of the Enterprise, which we looked up on Memory Alpha, it's about 300 meters. Mm-hmm. And then if we look at rocks nearby it, there's some that are slightly bigger, some that are slightly smaller, some that are in between. So we're saying average size of the rocks may be same size as the Enterprise-ish. Okay. I think that's a good
something like that.
Good estimate. And then
we then need to know the density.
Right.
Because how close is that? If you have the Enterprise here and another rock, the first rock is like super far away, not a problem, right? So it's got to be, I don't know, something like a third.
Yeah.
So you can fit 3 Enterprises between rocks.
Right, because like you said,
Okay.
if they're too dense, it's like a wall, can't get through. If it's
Mhm.
not dense enough, it's not a problem. I just go right through, and the scanners can penetrate too.
Yeah.
So it's got to be dense enough that it's dangerous, but not so dense that it's impossible.
Right.
And this seems
And so
like reasonable.
if I'm driving my car at like, okay speed, and
Mhm.
if I'm in my lane and then there's an empty lane next to me on each side and then a car, like I feel pretty comfortable, right?
Yeah.
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 So 1 kilometer in one way, but then we need volume. So we cube that up.
Yep.
So one
Sounds-
rock every kilometer. That's pretty okay. It's pretty small.
It's pretty okay. Yeah.
Okay, so then if we have the mass of each rock and then the density of the rocks in space, we need to get the total volume of the nebula, and we can multiply all that up. But that is a tricky number. So in Star Trek Into Darkness, they go from Kronos, the Klingon homeworld, to Earth in
Yep.
like it must be like a half hour or something. It's something fast,
Yeah.
which I think can't be right. It can't be right because that would mean it would be this nebula would be several light years in diameter, and
Gosh. Yeah.
it can't be right. That's enormous. That's enormous for rocks this size.
Yeah.
So
Yeah, so
let's
what-
make a low end guesstimate. Was that what you're gonna say?
Yeah, that's what I was gonna say. Is let's stick with the light year first
Okay,
and
so
see
let's
what
do a
kind of
low
numbers
end.
we get. Yeah.
Okay.
Because I think 1 light year is a low end because if the nebula was 1 light year in diameter, then the Enterprise could easily go around it.
Let's go around it.
Let's go around it. But we are unsure, so let's make this as the low end estimate and see what kind of mass we get.
100,000 million billion trillion quadrillion. So 9.4 quadrillion meters. So big. Sure. Big, but it's a low end estimate.
Right.
Okay, so now that we have the radius of the nebula, we can do a volume estimate, and we're not going to worry about that 4/3 in pi. We'll just cube it up. We have a cube nebula. That's fine.
Yeah.
But that's still 8.5 times 10 to the 47th meters cubed. What is? I have no concept of what this number is. It's so enormous.
It's so enormous. 10 to the 47. Damn.
But it's space. Space is big. Maybe
Space
that's
is
okay.
big. Yeah.
Maybe that's okay.
Yep.
Okay, so then we can now get the number of rocks. So if we have the density and the times the volume, we can multiply the volume by the density here, and so you get 8.5 times 10 to the 38th rocks. Again, an enormous number of rocks.
Well, what is a mole? A mole is times 10 to the 23rd.
Right.
So this is an absolutely gargantuan number of rocks.
Yeah. Yeah. 15. Okay. So, okay. But it's a number, whatever it is. I mean, my intuition breaks down. That's okay. We trust the numbers. We've had good arguments thus far.
Mm-hmm.
So now we can get the mass of the nebula. We just multiply this all together. So the number of rocks times the mass per rock. And so this gets us a number that is this. That is this. Just multiply all the numbers together.
Yep.
1.6 times 10 to the 49th kilograms.
Yep.
I have no idea what that is.
Yeah, it's just a big number.
So let's put this in some context here.
Yeah.
So let's look at Sagittarius A star. Sagittarius A star is the supermassive black hole in the middle of the Milky Way. I don't know if it's the largest. I'm not an astronomer, but it's a supermassive black hole.
It's huge.
Sagittarius A star. The whole Milky Way has gone around it.
Mm-hmm.
So that's 4.3 million solar masses. That's 4.3 million times the mass of our sun.
Yep.
Okay, so we're working in kilograms over here, so let's convert. So now we have 1 solar mass. It's 2 times 10 to the 30th kilograms.
I mean, first off, look at the comparison between the solar mass, which is times 10 to the 30th, and the number we got. The number we got is, what is it, times 10 to the 49?
49.
So
Yeah.
we're
Which is 19. 19 doesn't sound like a number, but it's 19 zeros.
It's 19 zeros times bigger than the sun. This is getting comical.
Oh, it gets worse. Okay, let's put it. Let's push it through. Okay, so Sagittarius A star is equal to this times this many kilograms, 36. So that means if I divide the nebula by the mass of Sagittarius A star, we get, what is this? Hundreds, thousands, millions, billions, trillions, 1.8 trillion supermassive black holes. That's 1.86 tera Sagittarius A stars. This is enormous. This is absolutely enormous.
And in fact, I think we looked it up. This is like much bigger than the mass of the entire Milky Way itself.
That's right.
So
It's more mass. There's more mass in this nebula than in all of the quadrants combined. All alpha, beta, delta, and gamma.
Yeah.
All the quadrants combined, there has less mass than this one nebula.
Yeah. So this is a statement about space is really, really, really big, and you cannot fill. You being like, I guess, God who created the galaxy cannot fill this tiny area, relatively tiny. 1 light year is super tiny on the galactic scale, with dense mass. You just can't do it because it's too much mass.
It's too much mass.
It's not just too much mass. It's like an absurdly large amount of mass. It would collapse into the most massive black hole of all time.
Yep. It should be collapsing into a black hole. Into many black holes, which then collapse into one black hole. Maybe. The whole quadrant is wrecked. Not the whole quadrant. The entire Milky Way is wrecked by this amount of mass here. Also weird. Now that I'm thinking about it, why are there rocks? If it's a nebula, shouldn't it be hydrogen, helium?
I mean, they called it a nebula, which when I think of a nebula, I think of diffuse hydrogen helium gas in like these
diffuse
big
meaning
bubbles.
like thin gas.
Yeah, it's like, I don't know the density, but it's like hundreds, thousands of particles per cubic meter.
If it was replaced with oxygen, you could not survive.
Easily, yeah, you would. It's essentially a vacuum for most applications.
Little bits of gas. Hear about
little
that,
bits
but
of
it's
gas.
mostly just empty.
If you need like a hard vacuum in the lab, I think it's not good enough, maybe. But I think for a lot of vacuum systems that we create in the lab, a nebula is plenty of a vacuum. So it's like slightly more gas than the rest of the galaxy. It is not like rocks slamming into each other.
So my thoughts are, if there's rocks, then it's not hydrogen and helium. So that means this is all star debris, because in order for there to be elements that are heavy enough to become rocks, that means it needs to have come from a star core. In which case, then shouldn't this be blowing up and expanding? I don't know.
But it's super weird, because in a exploding star, it's still mostly hydrogen and helium.
That's right. So when a star explodes, so if it's a small star exploding, then you get rings of hydrogen, helium, and then I think lithium is the next one. Yeah. You get rings that are sorted by their atomic mass, and then in the core you might have an iron core, or maybe a neutron core, or if it's a supermassive black star, you go straight to black hole. But in all of those, it's expanding outward. And
it's a gas or plasma. It's
a
not
gas.
rocks.
That's right. It's not solid.
Right.
Because for the rocks to form, it needs to be cool enough and dense enough for the atoms to form together. But inside of a star is hot. It's a plasma. So it's like individual atoms blasting out.
So there's really no way for this nebula to form, and it's wildly unrealistic in terms of mass and size. In fact,
the entire Milky Way.
This was an underestimate. This is a size that the Enterprise could easily just go bip around.
Right. This was a conservative estimate right here in this light year.
Yeah. And we could mess around with some of these numbers, but we would have to mess around with them at such a scale to get that number to anything realistic that I think we just have to declare the nebula itself unrealistic.
Which is the bummer, because it's super important that it be this dense and this large. Otherwise, nothing else happens in the movie.
That's right. They need it to be uncharted. They need it to be
dense, that you can't see through it, that you can't communicate out.
Yep.
It needs to be dense so that they've never been explored before.
Yeah.
Bummer.
Big bummer.
Okay, but cool though. I mean, also cool, like supermassive nebula that has more mass than the entire Milky Way. There's got to be some minerals you can mine from there.
Yeah. Maybe some ancient civilization was like, we're gonna make this, and then but the tech in the space was preserved, so it doesn't collapse into a black hole, and it's like spawning rocks from space.
Maybe this is some ancient aliens like trash hole. Just throw all this stuff here.
Okay.
Maybe I don't know.
They put an anti-black hole device right there, and they just throw their trash in.
That's right, because a black hole is how you go undo that. But if you have a impossibly dense region of space trash, yeah, you just keep it there.
Keep it there.